Making his way to the stage next is Nick Paulin from ERI. Nick has worked in multiple areas of ERI's broadcast transmission business, including engineering and design of FM radio and television antenna systems and of channel combiners for FM and TV applications. He spent the peak years of the digital television transition, a period of high demand and urgent delivery requirements, working at ERI's Gray, Maine manufacturing facility, producing television filter and multiplexer systems. Nick currently leads the RF engineering group at Electronics Research Incorporated and has been instrumental in introducing new products such as ERI's shared aperture FM antennas, low power FM and TV filters, and the FM all-pass filter. FM all-pass filter, yes. Nick graduated from Purdue University in 2005 with a BS ECET and joined the company later that year. He's a member of IEEE and AFCCE.
So here locally, we got the WAMU facility. So I'm just going to kind of go over that project. It's one of the more interesting cogwheels we've done. We do have another cogwheel that's being installed right now. I think it's actually being tuned today. But compared to this one, I kind of think that one's, I hope I'm not offending anyone, but it's a little boring. It's a 10-station cogwheel that's being installed in Cedar Hill, but it's all omnidirectional, and it's a 12-bay antenna that's top mount. This one here's got a few more features to it, so it's a little more interesting to talk about. So when this project started, they had to analyze the tower, and the tower itself wasn't going to be able to support the new antennas. So we had to do some existing, we had to reinforce the tower, replace the pole, do some modifications to the tower to make sure that the new cogwheel master FM antenna would stay on top of the tower. So the final configuration, we've got a cogwheel antenna with main facilities for WAMU, WPFW, WTOP as a directional, and WETA and WTOP. And then we also have a directional antenna, which is the WPGC, and then a non-directional antenna, which is the antenna below the cogwheel for WMMJ. So the facility requirements, WAMU, WPFW, WMMJ, and WETA, they're all non-directional. But WTOP and WPGC are directionals, and WTOP had to be able to operate in a non-directional manner on the cogwheel as well. So we've got the two authorized patterns for those two stations shown there. Those are the requirements for those two stations. One of those is on a rototiller that's on the top, and another is on the cogwheel. So the cogwheel itself, they're panel elements. They're mounted to a incorporated spine. So the screen, the support structure, it's all integral to the antenna, where the transmission lines and the antenna elements are all mounted. In this case, the clockwise input or right-hand CP is non-directional, and the counterclockwise input is the directional input. And this is just kind of another view showing the polarization inputs that are fed. So the clockwise, the non-directional, all the elements on the bay levels, or actually the faces as well, they're all fed in phase and with equal powers. Whereas the counterclockwise input, we've modified the power splits between the faces and as well as the phases to each of those phases in order to achieve the directional pattern. So the dual input antenna itself has a hybrid on the back. The element is mounted to a bracket that's mounted to the pipe, the support pipe. We sometimes call that the dog sled. And then the hybrid is mounted right behind the element inside the dog sled. And then the hybrid itself has 4 ports on it, 2 output that feed the antenna element, and then 2 input. One's the counterclockwise and one's the clockwise. Inside the element, you can see 2 balance. I don't know if this has got a laser pointer or not. I might just end up turning it off. So one of the balance feeds one slant of the element, and the other balance feeds the other slant of the element. And you can kind of see the topmost tube and the rightmost tube are feeding one slant, whereas the left and the bottom are feeding the opposite slant. So in with the hybrid feeding those two ballons, the ballon provides a 180-degree phase difference between the two monopoles. And when the hybrid feeds those two ballons, the hybrid provides a 90-degree phase difference to the two ballons. So as you feed the element, each monopole will have 0 degrees, 90 degrees, 180 degrees, and 270 degrees for one polarization. And then it's exactly the opposite for the other polarization with the right-hand CP. This is a rendering of the Empire State Building. It's just another panel configuration we did. This one was a 10-station and a 9-station combiner, right-hand CP and left-hand CP. It was slightly different than the WAMU system. These transmission lines didn't require any phasing. We did operate the top bay and the bottom bay at different power levels to achieve some null fill. And the auxiliary system was an N-1 over N array. So we had very little downward radiation, which was extremely important in this case because it's when you're standing on the observation deck there at the Empire State Building, you can look right at the antenna. And that aux antenna is able to stay on the air at full power for all 19 stations without overexposing the public. And that's a huge deal for that building because a lot of their income comes from that observation deck and very little comes from broadcast relative. So in this, the Empire State Building is a good example for what was touched on a little earlier with power handling and voltage handling, because there are so many stations and they're all running HD. So this is just a quick example. This is a 10 station. The example shows 5 kilowatt transmitters, which is actually very similar to what's at Empire. They're all between 5 and 7 kilowatts, all at minus 10 dBc. So you can see that with 5 kilowatts of analog, you would have 500 watts of digital average power for a total power of 5,500 watts. And then I'm showing the voltage peak formula there, which is the average power times the impedance. And then I put an extra 2 in there because without the 2, you get a voltage in RMS. So I'm adding the 2 so I can turn it into volts peak. And then, so if you run the analog numbers, you just have 5 kilowatts times your 50 ohms times 2. So you end up with 707 volts. And when you run the digital, you got to add that peak to average power ratio, which for IBOC is 6 dB. In television, that would be a factor of 7 for ATSC1, which is 5 dB, no, 7 dB. Or for ATSC3, it'd be a factor of 10. So the voltage is quite a bit more there. But even with IBOC, you can see that adding only 10% more average power, you're adding over 50% more voltage for the same station. So when you expand that out to 10 stations, you can see you're still at 55 kilowatts, which is just barely more than what 3-inch line can take, and you're still under what 4-inch line can take. But your voltage is so much higher. You're really, I mean, you're right at the limits even of 6-inch line. If you added one more station to this, you would exceed the voltage ratings of 6-inch line, and you'd only be at 60 kilowatts average power. So for transmission line, it's a big deal that we check this for multi-station systems. When it comes to antennas, we got all those power divisions, especially in panels. We got power divisions, but the voltage divisions as well, because the voltage only reduces by the square root of the power division. So if your power divides by 2, your voltage is only going down by the square root of 2. And usually at those power division points, especially if they're center-fed power dividers, you're looking at smaller conductors. And when you have a smaller conductor, you have a higher impedance. And as we know, when your impedance goes up, your power stays the same, your voltage goes up. So you got higher voltage on a smaller conductor, and you can run into a failure a lot sooner if you don't, that's why we check for it quite a bit. So back to the cogwheel antenna, WAMU. The WTOP directional pattern is on the left, and then the non-directional pattern is on the right. And you can see we got pretty good circularity out of the omnidirectional side for WTOP. Their TPOs do change depending on which side of the antenna they operate on. And then these are some of the patterns for the other 4 stations that are on the omnidirectional side as well. You can see over frequency, they do change slightly. At the lower frequencies, you got a little more of that triangular effect, whereas at the higher frequencies, you got more of a circle. So these are some of the shots that we took when we were still manufacturing it back at the shop. This one, we were able to actually build all 4 modules. And then you can see on the left there, we have a concrete stand in the backyard. We were able to assemble it and stand it up straight. We can't do this with a lot of antennas, but on this one here, we were able to. And we were able to test the entire antenna in its entirety before it ever left the facility. In the orientation it's meant to stand in. So some of the tower reinforcement and the antenna installation photos. Whenever these things arrive on site, one side of the cogwheel, the elements are removed so that when they pull these things up the tower, the gin pole doesn't get in the way and rip the elements off. And then those are installed after the fact. So for the antenna systems provided, we got 3 separate FM antennas. At the top, we've got the WPGC directional. That one was modeled at the range. We preferred that one to be at the top on this one because with directionals, you have to consider everything in the aperture space for a directional proof. And with it being at the top, nothing from the lower antennas are going to be inside that aperture space, so we didn't have to consider it. And then the cogwheel is right below that, and then the non-directional side mount sits below that. I'm going to go over some quick bandpass filter basics before I get into the WAMU filter. So each bandpass filters are composed of tanks. So, and when you look at a return loss trace, an S11, when you're using a network analyzer, each pole or each tank will contribute 1 notch in that return loss response. So it's pretty easy to tell from a measurement how many poles you have in a filter. And then each tank, as a circuit model, is an inductor in parallel with the capacitor, in parallel with the resistor, where the capacitor and the inductor will define the resonant frequency of that tank, and then the resistor can define what the quality factor or how efficient that tank is. When you're looking at, again, at the network analyzer trace, the top of the chart, this is usually the way you'll see insertion loss responses for filters. The top of the chart represents a perfect efficiency, which doesn't really happen in filters, not in real life anyways. In circuit models it does, but and then it's usually represented on a logarithmic scale, where every 10 dB is a decrease in power that can get through the filter by 10 times. So at 10 dB, on the skirt there, where you're at 10 dB down, you got 10 times less power that can get through the filter. Once you get to 20 dB, it's 100 times less power that can get through that filter. And then it keeps going out from there. That's the general efficiency formula, and that can be used for filters or it can be used for transmission line. It's pretty versatile, and you can actually use it both ways. So you can, if you start with your TPO, you can use a negative dB value to get past your filter to see what you got on the output of your filter, or you got a measurement on the output of your filter. You can use a positive dB if you know your insertion loss of your filter and you get back to your TPO. So this is probably a chart that most people haven't seen because we don't look at bandpass filters this way usually. So this is a 3-pole filter that's been tuned to 98 megahertz. And so you can see on the very far left, there's a spike. I've got a marker there at 98 megahertz, but the span on this measurement goes all the way up to 1 gigahertz. And this is just kind of show that bandpass filters work very well in the band. So that's why we use them for channel combiners and combining transmitters into antennas. We don't use them to suppress products past second harmonic. If you think about the physical construction of a filter, we got the resonator inside of the tank, and those are usually quarter wave resonators inside of a tank. So at FM, they're about 30 inches long or so. Well, because RF is cyclical, FM would radiate or resonate again at 3/4 wavelengths and 1 1/4 wavelengths. Well, if you think about what happens at say 300 megahertz, well, an FM resonator is third harmonic at 30 inches. So it would resonate on a 30-inch resonator. So you start to get these secondary pass bands in an FM filter just because of the physical constraints of the resonators. So you can see, even harmonics, you can get some suppression, but odd harmonics, you're not guaranteed to get anything, which is why that all transmitters come with a low pass filter built in. They clean up everything in the harmonic range. Whatever you get out of the band pass filter is just kind of gravy. So the construction, we use inductive loops. So this is one of our loops in our bandpass filters. We silver plate these to reduce the losses, keep the quality factor up. These types of loops work very well in modular cavities. Other types of coupling you might see, space couple, that's pretty common. Even in FM, like an interdigital filter would be a type of space coupled filter. There's capacitively coupled couplings. Those are usually some sort of copper disc that can move between the resonators to help encourage coupling between the resonators. And then there's direct tap coupled filters. And those are really more common in like a low band VHF television or high band VHF television. And there's kind of a tier list of how strong the couplings are, like a direct tap coupling directly to the resonator where you physically connect your interconductor to your resonator. That'd be the strongest coupling you can get in a filter. And then your inductive coupling, which uses a loop similar to this, and there's various different approaches to doing this. Those would be the second strongest. And then your capacitive coupling would be the weakest of the three. So just kind of depending on what is required to generate the response in a filter would kind of dictate which coupling you use. And then I mentioned the resonators. This is a copper resonator inside of a filter, at least the end of it. Almost everyone has moved to INVAR using, for temperature stability. So there's an INVAR rod that goes down through the center of the resonator. It gets attached near the top plate of the filter and attached to the end of the resonator down here where we have a corona ball. So with temperature, hot or cold, metal will shrink or grow. So filters usually warm up when we apply power to them. So the copper will end up growing. So what this does is it allows the copper to grow, and it grows into those bellows, and the bellows takes up the expansion of the copper, and then the INVAR keeps that resonator at the same length over temperature. So it keeps everything stable. And some other manufacturers, will use some forms of either finger stock or machine fingers. There's several approaches. We've used bellows for the last 20 years, and we've been very happy with it. So when you look at the different types of filters, and earlier it was kind of touched on manifold filters and reflective filters already. I've got an example here with two co-located arrays. I just call them System A and System B. And these arrays usually have more than 10 feet between them, so there's some inherent isolation between the arrays. They're physically separate arrays. So if you have a change in one array, it's not going to affect the other array. So like a reflective or a manifold filter in this case would be appropriate. Now in a situation like this where you have a panel antenna and you have a reflective and a manifold filter, now a change in the antenna will affect both arrays. So the isolation is highly dependent on the tuning of the antenna. So if anything in the tuning of the antenna changes, your isolation could change dramatically, which would mean that power from station A could go down the pipe, couple across, and down to the filters of the second chain. Now, that's not necessarily a bad thing, but in this case, reflective filters or manifold filters, if you look at the termination, they're short circuits. And when you put power into a short circuit, what does it do? It bounces back. So what it's going to do is going to bounce back up. It's going to go back up to the antenna. It's going to re-radiate, but in the opposite polarization. So, I mean, your mileage may vary on this, but you have the potential of even self-interference, you know, especially in low signal areas. So what we usually recommend in situations like this is constant impedance filters. So you got the same, you know, potential problems with the isolation, with changes in the antenna system, but this time, if the power comes down, it's gonna bounce off that second set of filters, and it's gonna go into reject load and just be absorbed as heat, and it won't have the opportunity to go back into the antenna and re-radiate as self-interference. So this is just kind of a summary of what I just talked about. You know, it was mentioned earlier that T's and manifolds are lower cost. They're usually smaller footprints. One of the cons, and this comes up occasionally, is that they do all have to go in kind of the same location because the spacing, those line sections between the filters is all critically spaced. You can't just put any line length in there. It has to be tuned a certain way. After they're designed, they're not easy to rearrange. They're not as easy to expand later, but with some engineering work, it's not impossible. It can be done. ERI likes to rack a lot of filters, especially in tight floor space requirements. So T's and manifolds are a little harder to rack because you got those critically cut transmission lines you have to try to get exactly right in a vertical rack, and it's just a little harder to do. And then in dual input systems, the short circuits can reflect the unwanted energy. Whereas with constant impedance, you know, it takes care of the reflected energy. They can be placed in different rooms, and that's happened from time to time where a station will want their own filter in their transmitter room, and then they just plumb transmission line from room to room until they get to the antenna input. They are very easy to rack. They've got a little better synergy with dual input systems, but it all comes at a cost, and that's twice as many filters and hybrids, and they do take up more floor space if it's a floor mount system. So since WAMU is a cogwheel or a panel type system, and they do have two inputs, we did opt to do the two constant impedance filters. So on the left-hand side, you have the WAMU, WPFW, and the WETA combiner modules, and WTOP. So WTOP actually has two combiner modules. The one on the left is part of the omnidirectional input. And, you know, this is 4 stations, so all of the voltage calculations we talked about before, you know, with the transmission line and the antenna, that all, you know, we got to do it all again for the filter too. Usually the failure point in filters with voltage is inside those hybrids. About 15 years ago, we went through a cost reduction exercise to reduce the cost of our hybrids, and at the same time, we were able to increase the voltage handling of our hybrids. So it was kind of a win-win all around, and that served us pretty well, especially since when IBOC was allowed to increase their power. On the right-hand side, we have another constant impedance racked module that is feeding the directional input of the cogwheel, and then there's a reflective filter there for WMMJ, and like I said earlier, they've got a separate system. It's a co-located system, so they're just using a reflective filter. This site was, the building was actually built for this combiner. So we had all the room requirements. It was built underneath the tower, so everything was pretty tight to move things in. I'll have some pictures on that later. And that is, so, you know, we fully assembled everything and tuned it to ERI in its final format there. Real quick with the patch panel and switching system, a couple of stations, you know, they can switch around between antennas, especially the station with 2 antennas and the various inputs. Mostly the patch panels here, they're they're used as basically a lockout tagout system. They don't really patch them around. If work needs to be done on the antenna, they can just remove a U-link and they're off the air. So it's kind of peace of mind for the tower crew. They see those U-links out, they know they're not going to be radiated. So here you can see some of the boards that were put down. That was the area we had to get through in order to move the filters into place. And he's going to be able to speak more to this. He was actually there. I was not. We had a full crew putting all this in. And these are actually some of the shots back at the factory. At least those top two are back at the factory. The bottom two are at the site. So like I said, we had the complete room plan of this building, and we just put tape on the factory floor and made sure everything was going to fit before we shipped it out there. That's the crew that's there. Andy was there, I wasn't. But Tom was out there, Keith, Jeff, Troy. Rob was still there. Any questions? Yeah.
Hang on one second.
Yes.
And this is not trying to catch you, just if you have to remember. On the cross-coupled or on the polarization, were you able to get 30 dB or something close in terms of isolation? You just off the top of your mind, do you remember?
At some frequencies, yes, not at all frequencies. We usually use a planning factor of about 20 dB.
Just this is less about the antenna and more out of curiosity. How do these various transmitters deal with dummy loads? Do they put switches ahead of the combiners basically, or?
Are you talking about like a station test load or?
Yeah, well, if you've got a problem with your transmitter, you want to run it into a dummy load to make sure it's a problem with the transmitter and not the antenna.
There's nothing in the combiner room. Andy, there's anything in the transmitter room?
So at the AU tower site, every tenant room, they basically are, if they want to have a load, they can have it in their room. There are no loads in the combiner shelter. So everybody has, well, other than the reject loads and the dump loads and things like that, that are part of the combiner system. But otherwise, tenants are required to have that on their own. Some tenants share through having some RF switches in the space. If they have transmitters in the same room, they can share a load, for example. And only a few tenants do that. That's the AU site. I think many shared sites do something similar.
Just to the same question, at WETA, we actually have not only loads for the transmitter, but we also have a load at the very exit of the building before it goes up the tower to the shared antenna, so that if we need to, we can test the entire system with everyone's transmitter turned on into a known good load.
This is kind of an off-topic question, but having worked at this site for quite a few years, this is where this is coming from. Historically, the tower and the building next to it had ground problems. Was that a factor in this design build at all?
I don't remember.
No, I mean, so we did have the ground system looked at and beefed up a bit as part of the tower project. So we had, the ground strap better connected to the tower in this case, and we had things looked at. But grounding was not an issue in this case. Yeah.
All right, Nick, thank you very much. Let's have a round of applause for Nick.